So thanks for introduction. Hello everybody and welcome to my PhD seminar. Today I want to summarize what I've been working on it since 4 years ago in next 30 minutes. My thesis study on robust observer design for a class of nonlinear systems, LMI approach. So let's get started. So the first slide, I want to give you a big picture of the automatic control if you're not familiar with this topic. So there is a clear analogy between human body and a control system. As an engineer, what we do in control engineering is that we do control theory to do some magic to make the system achieving the satisfactory condition. So we will take these things into consideration, and further we will talk about it a bit later. Just think about a human, that how we grab a bottle or a can from the desk. So we are using some sensors like our eyes and our controller, which is our brain, and we do some process like the trajectory to grab that can. And to do so, we are using our muscles as actuators. So similarly, in control system, we have the completely similar things like a controller, which is, in our example, was our brain, sensors that we are using, like our eyes, and the actuator, which is the part of the process usually. So, but in my thesis, I'm focusing on the virtual sensor design. So I use this term virtual or observer because in order to understand how a plant works, we need to access to some quantities that sometimes they're not basically measurable. So what we do, we try to design a virtual sensor to estimate those quantities. So that's why we are focusing on the observer, but simply observer is a dynamic system to use the measurements and the inputs. We will take a look later, a bit more scientific definition. Use the input and the output and give you an estimate of your system and state. I said state. What I mean by state variable is the smallest subset of the system that can describe the entire system. So if we take a look, it means that your current state is an equation relating to the history of the system and the current input. So, but the thing that you see in the green color is the main focus of this talk actually, which is the robustness of the observers. So we will deal with that more and more. So consider the system dynamics, as you see here, which is the function of the state vector or state variables. The parameters of the system can be function of the time, input, and some disturbances, which is the omega. And this system is basically initiated with some values, which is x naught. So I borrowed this definition from Misawa 1988, that the state estimation problem is designing a dynamic system that can estimate the state x given the measurements of y and u are available. So simply, this is the fundamental thing in state estimation, that you have a estimate of your state and you define the estimation error and you try to minimize this error in some sense, depending on your problem. So let's take a look at this simple example, mass spring damper, and put whatever I said until now to this example. So think about the mass spring damper, and writing the Newton's second law, you can see that we will end up to a second order differential equation. And taking two variables, the position of the mass and the velocity of the mass, and the input, which is the force, the implying force, you can end up to this state space realization. So now the question is, you see that we are assuming that we can measure the first state. So considering a perfect measurement of the position of the mass. So now the question is, can we estimate the second state, which is the velocity? So that's actually the point of having an observer in your system, which is capable to give us an estimate of the second state. So observers can be classified in from different perspectives. Observers can be linear or nonlinear. Based on what we are, the designer, interested in, we can be interested in the entire state vector, like the previous example that I showed you, the position of the mass and the velocity. Or you can say that in case of having perfect measurement of the first state, which was position, I'm just interested in the second state. So in that case, we can go for the reduced order observers. Observers can be designed for stochastic or deterministic systems. But in my thesis, I'm focusing on these properties, nonlinear system, full order, and reduced order for the deterministic and stochastic system. So, yeah, we will deal with these terms until the end of my talk. But just to give you a big picture of my thesis, it's an observer design from the robustness perspective. So what we basically do is that we try to design an observer which is robust against some unwanted guests in our plant. Can be process noise, can be measurement noise, and we're assuming that the process sometimes can be uncertain and can be delayed. So we will focus on all these terms in some specific realizations, and we will deal with that to see how we can design an observer for that. So we will get back to this figure over and over. For the first case, let's think about a very simple linear system that you have the state space realization follows. So observer is simply, the Lewin barrier is a copy of your system, as you see the first two terms here, and the corrector term. And as a designer, if you write the aerodynamics, you try to find the error, satisfying this equation, and make it asymptotically stable. So what I mean by asymptotically stable is that think about a working point, which in our case is the origin, and take a ball around that working point. And within that ball, if you pick up an initial value, asymptotically stability means that after some time you will get back to, you will converge to the origin. So in that case, you have a good estimation. But unfortunately, this is not the only case. You might pick up an initial value and see that ball, but stay again somewhere around that ball forever. So in that case, you have the stable, or in worst case, you might get out and you'll never come back. So unstable aerodynamics. For the linear case, we have a theorem here, as you see. We say that for matrices L and positive difference P, if you can solve this inequality, which is linear, you can guarantee that the estimation error will converge to zero asymptotically. But in this case, the question is how to solve this inequality. So here is the first place that I want to stress you that this linear matrix inequality, that the LMI history dates back to 1890, when Lyapunov was working on the energy, and he suggested, he was working actually, I don't know I'm pronouncing correct, Lyapunov, you might know better. Oh, you would mind, that's true, that's true. So yeah, so that was the first place that people solved that how to solve an inequality. So for simple cases you can solve it analytically, but for large dimensions of the system it will be definitely a hard task. So for the LMI, so this is simply, if we take this word LMI, linear matrix inequality, so it's simply this structure. For LMI problems, basically you have two different things. Your problem might be feasibility problem or might be optimization problem. So in feasibility, what you do is you try to find the X satisfying your inequality, and that's it. But for the optimization, you might be interested in optimizing, like minimizing a cost function with respect to some matrix inequality. So as I said, for simple case, it can be done analytically, but for high orders, you definitely need the numerical techniques. But what are LMIs used for? So many engineering optimization problems can be, should stress you, not always and not easily, translated into LMI problems. So it can be LTU, linear programming, quadratic, or robust control problem. And in this thesis, I'm working and focusing on the robust observer design and how we can translate this problem to LMI. So let's take a look at this Lyapunov inequality, or let's call it the inequality. So we have two constraints here. So our point is how to find a P satisfying both inequalities. So my point here is that you can simply translate, when you translate your problem to LMI, you can simply write it in if you're familiar with the MATLAB software, so in using the Almond toolbox and using some solvers, and you see in a couple of lines you can simply solve it. A better information and a bit more complete information about this YALMIT and solvers you can find in the thesis, or directly go to the YALMIT wiki by Johan Lofberg, so you can find more information there. So up to now we talked about the linear system. So let's talk about the nonlinear observer and how we can design a nonlinear observer, but LMI approach. So think about the nonlinear system, and you see we have a new guest here. As Sophie said, that Lipschitz function, that it, this kind of nonlinearity should satisfy this inequality. And in this case, for example, take a look at the left-hand figure. So it's on the left, you see that it's usually trigonometric functions can be described as a Lipschitz, and you can simply find a gamma which can define and satisfy this inequality. And but sometimes, this is a global Lipschitz function, but sometimes functions can be locally Lipschitz. So you define a domain and you make it, you find the proper gamma in that domain. So in that case, it will be local Lipschitz. But sometimes your function can be non-Lipschitz, and we're not able to find the proper gamma for that. So similar to the linear case, we can design an observer, again a copy of the system and the corrector term, writing the error dynamics, and propose a theorem based on linear matrix inequalities to find the observer again L. As you see here, the black color shows that these terms are similar to the linear case, but due to the nonlinear case, you have some blue colored terms. You see here. Has been added on to this inequality. But again, the final product is an LMI that you should solve and get a feasible solution to. But now the question, is it the only way that we can find out? Answer is no. Sometimes you can propose less conservative conditions like so, and again try to find a feasible solution to. For example, this is the main focus of our paper C, that we will deal with that a bit later. That's how we can propose a less conservative condition. Let's take a look at this example, single leak manipulator, that you have the 4 state variables for this nice and interesting plant, the angle of the link and the angle of velocity of the link. And but since the link is flexible, the angle of the link and the angle of the DC motor implies is a bit different. So here is the state space realization using the theorem that I showed you before, and using the Yalnick toolbox instead of the solver, you can simply find the observer gain L. And here is the two states, the solid line and dashed line is estimated. I just want to stress you that if you use the first inequality, you will never get a physical solution through. But if you try the second inequality, which is less conservative, you will end up with this solution. So this is a good example to show that it's better to have less and less conservative conditions. So again, we get back to this figure. This actually figure that I said it's a bit wrong in the thesis, so here is a bit better. So the question is, for the uncertain system and the topic that we are focusing, robust observers. So here, for the first part of our thesis, we are looking at the uncertain delay system and how to design an observer robust against uncertainties and against process measurement noise. But you might ask that why is it important to focus on the time delay? Because time delay is always a guess in our process control. Delay might happen in state, might happen in input, or might happen in the output. And delay might be a cause of instability in our system. So just give you a better understanding of the time delay and examples. Think about the network control, that you have a plant and you have a controller and you're communicating through the network to control your plant. So the time delay might happen in the measurement in the process and in the actuation. Or for example, in steel rolling process, you have the sensors and you have the measurement delay in your you have a delay in your measurement. So and in for example, here we have a steel mill in Luleå. So, but again, to give you a better understanding, this I think everybody experienced this, that for the temperature control you have the time. And personally, I experienced this morning. I was thinking about this and so that's the example of the time delay. All right, we'll continue. Another example to show you that uncertainty can happen in the process. Think about the double tank process. You see here, and think about that at least in lab scale, the outlet of the outlet area A, small a, can be measured, but including some uncertainty. So your value might be uncertain. So that's why you have a delta variation around this parameter. But this system realization can be translated into the following structure and matrix decomposition. But now the question is, well, why do we need to write it? This is the common and popular matrix decomposition in robust control that we will deal with that in paper A and B. And again, think about having a time delay, no matter you're using state feedback or output feedback. So think about the time delay in your input. So definitely you will get some delay in your system. So yeah. So in paper A and B, we're focusing on this quite general system structure. I say quiet because it is quiet. General system realization. And we're assuming that the time delay is also uncertain but bounded. So, and you see here that the matrix decomposition here, which is fit with the previous example, if you ignore some like delta CT. So, in those papers, we worked on this general system realization. We worked on the unknown time delay, was bounded, we look at the robustness issue of the observers, and we try to translate our problem to linear matrix inequality problems. And in the last step, we propose a multi-objective optimization problem. We have different objectives, two objectives. We try to minimize the noise impact on the observer performance and to maximize the level of the uncertainty, and take and find some curves, the trade-off curves to tune the level of the uncertainty and the noise impact. So, and these are the references for this part. Let's move on. From another perspective, your observer, it would be very nice to be robust against unknown inputs. So again, we will take a look at this example, the double tongue process. So think about that. You're measuring the height of the second trunk, and you're basically estimating the both height. And what happens is that if somebody comes and opens the valve of the lower tank, your observer fails. And the type of the observer that you can design be robust against this kind of unknown inputs, or unknown, I mean, it's called unknown inputs observer. So I just follow these figures from my thesis, and the whole example is that here my point is that think about the estimation in general for the linear case, for example. So you have a true state, a solid one, and the dashed line, and you see the good performance until the time 13 seconds. But what happens is that if you have a disturbance in your system between the time interval, 14 to 16, you see the observer performance fails. So it's not a big surprise, because this is the structure of the system. But we are still designing an observer for the plant without unknown input. And this is the time delay. This is the error dynamics that we try to find L to make it asymptotically stable. But we are missing this term, the unknown input. So that's the part that deteriorates our observer performance. So for the nonlinear case, also the same story. But here is the observer, or this developed structure for the observer. And you see that I made the blue color for the linear case, and the red one, blue plus red, for the nonlinear case. So here's the structure. That the problem is now how to find the gains N, G, L, M, and E. So this is the general algorithm for unknown input observer design for nonlinear case. So you try to find the Lipschitz constant gamma and do some mathematical calculations. But here is the product, which is the linear matrix inequality that you have to solve and get a feasible solution to. And through that, you can find the observer gains. So let's take a look at this example. We are using the steps, 5 steps here for the discrete time system. That actually the approach was introduced in paper C in ECC 2014, which is less conservative to the previous one. So in this case, think about the crane system here at our laboratory. That you have the 3-state, the absolute angle of the cargo, and the velocity of the angular velocity of the cargo, and also the bias coming from the gyro measurement. So, and here is the state space realization. And going through the 5 steps, so you will find the good observer performance here, and which is robust against the unknown input. So up to now, I was talking about the estimation and unknown input observers, but why not looking at the problem of the unknown input observers plus reconstructing the unknown input? Can we do that? But the first question is, why is it important? Because if we are able to reconstruct the unknown input, we might use it in the disturbance rejection in control problems. and it's definitely useful in fault detection and isolation. But now the question, can we do that? Yes and no. Yes, because we can do it, but under some conditions and constraints. So think about this state space realization. It's the general case. The trick is how to rewrite the structure, the realization to the descriptor system, that the new state variables are the state vectors plus the unknown inputs. So, and we will try to follow our, to observe a structure and find some LMI conditions, solving them, getting to feasible solutions. You are in safe side and your observer watch. So in paper D and E, we work on that structure that showed you in previous slide. And again, we're looking at the problem of the robustness of the observers. And we try to provide some conditions in terms of LMIs, easy to solve, and satisfying those conditions can guarantee you the asymptotically stability, the observers, aerodynamics. And finally, we try to convert the problem to multi-objective optimization problem, like I said before. So look at this example that we use in that paper, that chaotic Schwarzschild system is highly nonlinear system, and you see the trajectories, the tractors of the system, and you see that not only we are able to estimate the state variables, the three states, we are also able to these will constrain some unknown inputs entry into the system. So yeah, in the last part of my thesis, I was looking a bit different in the problem, looking at the control structure and observer-based control design. So here I discovered that I definitely need some constraint on the unknown input, and I assume that it's bounded. And in the way of the observer-based control structure, I found some linear matrix inequalities and some conditions that satisfying getting feasible solution through those inequalities can help you to find the observer gain and the control gain. And you see that, again, I'm using the previous example, Schwarzschild system. And you see that after 50 seconds, we are implying the control action, and you see how it behaves and makes the system converging to the stability actually region. And this is the zoomed version of that you see the stability region. It's around the origin 0.05 up and down. So yeah, and these are the papers actually published for this part of my talk. Right. Let's move on. I'm about to finish my talk. So for the future work, this is the things that I'm working that can be continued, and this is actually my mind path. See, not so many noise. And what I have done is basically on the nonlinear systems, and I'm assuming a class of nonlinear system, Lifshitz function. But why not looking at some more general system, nonlinear system? For example, one-side Lifshitz that some researchers are working on it. And I've been focusing on the parametric uncertainty in our system, but why not looking at the other parts of uncertainty in your system? And the things that you see in the yellow color, these are the things that currently I'm working on it. Why not looking at the problem of the nonlinear systems and observer design, robust observer design for them from completely different perspectives? Why not translating the nonlinear system to linear parametric varying systems and using the linear approach for that? And for the hybrid system, whatever I said and I talked today, and you find it in my thesis, is either continuous or discrete. Or why not combining all these things and make it hybrid, and for a subclass of hybrid system switching systems that I'm working on it. Another thing is that I showed you in one slide that how important is having a less and less conservative conditions. So why not make the unknown input observer less conservative and make it a bit relaxed and make it a bit more suitable for the practical thing? And I see a good potential in the time delay and the fault detection for further investigation. So, right. So, and here's the place that I want to conclude what I said today and what I did in my thesis. So I've been working basically in the time delay system, unknown input observers, unknown input reconstruction, and looking the lab part of my thesis and the control, observer-based control system. And for each part, I've been looking at the robust observers and see that, for example, for the time delay, without having access to the certain value of the delay, just having some knowledge about the bound of the time delay, how can we design the robust observer? And in all cases, I'm suggesting some LMI-based conditions that you can simply solve it, and if you're lucky and get physical solution, you can enjoy your life. So nothing left, just saying thanks for your time and attention. Thank you very much.